Só lá? Beleza. Our next speaker is Paulo Mendes. He is a PhD student here at IQSC. Paulo, take your time.
Okay, thank you, Jonathan, for the introduction. So just open my slides here quickly. This is it. Pitchy. Okay, so very nice to have everyone again here for our fourth workshop, some new faces too. So welcome everyone, thank you for your presence. Today I'll talk to you about some developments about the adsorption of carbon dioxide on transition metal clusters and nanoalloys. I will focus mostly on nanoalloys. This project is supervised by Juarez da Silva. I am Paulo, and most of the results we had the collaboration of Lucas and Viviane. Also, I'll show some results from Chris, but our team is big and we have several people working with different projects involving CO2. And I would like to, beforehand, thank all the funding agents, our institutions, and the center, and our group, QTNano, and your presence. So the question about carbon dioxide, we will attack this problem from the atomistic perspective. Okay, we will talk about it from the atomistic level. And this problem has been around since the 1950s, maybe even before. And we know that it can physisorb or chemisorb. And how do we go about improving, advancing this knowledge? It's quite a challenge because it has been around for some time. But one of the ways is to convert CO2 into other moieties, different types of chemicals that can be used for different things. Imagine being able to capture and convert CO2 using a catalyst. In this case, I will propose here transition metal nanoparticles. But imagine being able to convert CO2 into different things that can be useful, like monomers for plastics, moieties for the pharmaceutical industries, fuels. And the first step to conversion is adsorption. This is what I will talk about. Lucas told us about, in the previous talk, about the environmental impact of this transformation. I would like to call your attention for the economic promise that this means. Even if we don't solve the climate change problem entirely through these types of conversions, the economically this is marvelous because the abundance of carbon dioxide is extreme in our atmosphere, but not so much of carbon, sorry, the carbon element is not abundant in the Earth's crust. We have only at most 1% of abundance of carbon in the Earth's crust. So if you can harness and use this carbon from the atmosphere, this would be marvelous. And we will propose to use transition metal clusters made of these transition metals here. But the problem is that they can have several sizes, morphologies, compositions, a lot of properties that affect the catalytic properties, and they can all be tuned towards optimal properties. So we want to provide ab initio insights in the adsorption of carbon dioxide, and I will focus on the alloying effects. And before talking about the alloys, I will bring some of the basic knowledge that we had before starting this project. These are results from an article by Viviane Ocampo Restrepo, and the authors showed us that what happens, they confirmed through density functional theory, what happens with carbon dioxide when it bends. When carbon dioxide bends, we say that it's chemisorbed if it's adsorbed on something, and the relative energies of certain orbitals, of certain states, electronic states change, and the angle will be smaller than 180 when you will increase the charge of on CO2. So this has been attributed. The bending of CO2 is attributed to either charge or electronic excitation. And Viviane studied these systems from 3D metals, and she found that for small clusters, 13 atom clusters, the type of metal is one of the most important things to affect if CO2 will bend or not. On copper, it does not bend, and on the other metals, going to the left on the periodic table, the carbon dioxide bends. And this is an additional study for 4D metals this time by Cris Batista and other authors. And she studied not only the putative global minimum configuration of these 13 atom clusters, but also icosahedron clusters that are model structures. And she studied, this is the adsorption energy with different compositions for the putative global minimum and the icosahedrons here. And the silver cluster did not bend CO2 easily, while the other elements to the left of the periodic table bent CO2. And she studied the correlations of, between several properties and found that, for example, the adsorption strength measured by the adsorption energy is correlated with certain other properties, such as the charge transferred. So when more charge is transferred to CO2, the adsorption is stronger. That's the basis of chemisorption. And the distance between the molecule and the substrate also is shorter because the interaction is stronger. So this is just to situate about our previous knowledge before starting my studies with the group that are about size effects that Lucas also already showed you. And I will talk about the part concerning nanoalloys. So the nanoalloys, if you were here in the previous workshop, you remember that I showed you information about how these nanoalloys are formed. These are platinum-based nanoalloys, and they came from model structures. So we have various different morphologies, and we have two types of compositions. One containing 13 platinum atoms, and the other with 42 platinum atoms. And all particles, they have 55 atoms. They have this constraint. And we proposed the model that is published in this article here, Journal of Physical Chemistry, that with this model we can predict which type of morphology and chemical ordering will be formed. So if we think about using these nanoparticles to adsorb CO2, the possibilities are very rich, they are numerous. And how do we go about studying this? So our goal in this project is to understand this adsorption on these very different alloys and compositions. So I would go directly to the results for you. These are results from density functional theory. And sorry. How does CO2 bind to these nanoalloys? It can bind in very different ways, depending on the nature of the nanoalloy, depending on its properties, which is very beautiful because the catalytic properties will depend on the atomistic level properties. So, for example, I separated here for this talk in two types of regions. You have homogeneous regions that are composed of platinum-platinum adsorption sites or transition metal types of adsorption sites. And in these types of sites, the carbon dioxide will bend, will activate only on low coordinated sites. Otherwise, it does not bend easily. These dashed lines here show a large distance between the molecule and the nanoclusters. But in heterogeneous regions involving the two types of metals, the alloying effect takes place and charge transfer seems to be easier in these cases, and carbon dioxide almost always bends on these types of sites. So the site preference and the effective bending of the molecule depends strongly on the way that you conceive your nanoalloy. Okay. So I picked up two examples here to show in these graphs to talk about the performance of the substrates for CO2 activation. So in here I have these symbols. I have the unary systems in circles, less platinum with squares, and more platinum with triangles. And I have cobalt and copper. Copper, if you remember well, it does not bend CO2 as easily as the other metals. So this is one type of behavior, and cobalt is the other behavior. The solid symbols are the lowest energy configurations. And we can see that the angle with the adsorption energy has a trend here. For metals such as cobalt, when you have the unary system, this solid circle here, the adsorption energy is very negative. It's more stable. It's a strong adsorption. But when you add platinum to the system, you still bend CO2, in this region here, but the adsorption energy is not as strong. But with copper, you see the opposite effect. Copper alone, if you bend CO2 on copper, the adsorption energy is not strong at all. This is not stable. But if you add platinum to the system, the adsorption is stronger. This is favored. So it's favored by addition of platinum. So CO2 activation can be controlled through alloying. And these are the interaction energies that they consider the effects of deformation of the geometries of CO2 and the clusters. And you can see the two types of behaviors and the strength of interaction changing according to the platinum content. For example, in copper here, you have a weak interaction. So the more negative this number, the stronger the interaction is, and it increases the more platinum I put in the system. So what else can I tell you? Let's talk about charge. Charge is the effect that is responsible for this result that we see of bent CO2 on our structures. So these are electron density differences, these pictures here. And you can see the numbers are the charges in each system. I chose a limited set of systems just to represent things. And you can see that there is a trend, there is a type of periodic trend along the transition periods. If you go from iron to copper, you have more charge and then less and less charge as you go as you fill the D band, the D states. As you fill the D states, you will have a different behavioral charge. What else? For physisorption, the charge is almost constant. It doesn't really matter the type, the alloying effect. For the core shell type of systems, you have a certain trends too. In the physisorption case, you have almost no effect, no charge transfer. But when you have different types of metals, you have the periodic trends too. And these trends are different. If you have few platinum or more platinum, this can be studied in more detail. And here are the interaction and adsorption energies for the systems, but they are just to show some periodic trends that also happen for these systems. And here I have the chemisorbed and physisorbed states mixtured, but I only show the most stable condition for each case. And what I want to show, to call your attention more, is this picture here below that shows the type of the orientation of the molecule with respect to the cluster affects the bond stretching of this bond stretching. This can be a symmetric stretching, just like here on the right. These bonds, they stretch equally. But if you have configurations such as this one here, this bond that is pointing away from the substrate, it doesn't stretch as much as the other bond that is quite spread, that is spread around the edge of the cluster. And this is a very important effect, mostly governed by morphology. Depending on the morphology of the particle, you'll have different edge sites that can allow this type of configurations. And this can be very important to allow different reaction pathways. If you have one of the bonds that's much more stretched than the other, then you can be favoring another types of reaction pathways. Also, in here it's difficult to see. I went back one slide, but it's difficult to see because it's small. But in cases such as this one here, you see an accumulation of charge in this edge here. And this can affect the co-adsorption of another species. If you have CO2 already there, so how will other species adsorb? The way that the density, the electron density is rearranged with adsorption could affect this, and this could be important. So what can we take home from these results that I showed you? Alloying with platinum can enhance the adsorption strength of CO2 nanoparticles, or it can have the opposite effect depending on the type of metal. The presence of heterogeneous environments is usually good. It usually facilitates the bending of the molecule. This is mostly attributed to charge transfer. And the type of adsorption is controlled by the capacity of the nanoalloy to transfer charge to CO2. And when you make the nanoalloy, the charges will be governed, will be driven by several effects, by the exposure to the vacuum region, by the electronegativities of the elements, okay, the interaction between specific regions such as the core and the shell, the magnetic moments of these regions will all affect this process. So it's a very, we have several effects at the same time to show us these final results. So alloying should be accompanied by evaluation of other properties, other types of features, such as the chemical ordering. How are the elements distributed around the nanoalloy? Are they homogeneously distributed? Is it a core shell structure? And it can be understood in detail from the atomistic level to provide insights for experimental research. Now, this point here is cool because I will ask again, how do we advance this knowledge now again? Because it's never enough, right? We reached a certain point, but we always want to advance more. In my opinion, I think that the marriage of these types of results with experimental results will be a way to move forward. We are in a situation like a heaven and hell situation. That story where you have people tied up with big spoons, and the difference between heaven and hell is that in heaven, people feed each other. You can't feed yourself, but you can feed the other guys. So I feel like this is the situation where we are at. Kalini asked an interesting question about the experimental side, and to be closer to heaven, I think we will need this. We will need to marry these results with more experimental data, but we are worried with the consistency of our calculations from the beginning, from the moment that we start studying the clean substrates. Each one of the particles is carefully studied comparing with experimental data. We have their magnetic moments, their binding energies, their the average bond length, everything is compared to experimental. But when we talk about a practical problem, such as CO2 adsorption, and we want to talk about alloying effects, I think to really advance further, we need this collaboration between experiments and theory. And that's what I wanted to show you. Thank you again, everyone. That's it.
We are now open for questions.
Hi. When you talk about a charge, calculating charge, the interesting point is that we have several methodologies that can generate these charges. And in general, they can have a different description of what you are looking for. So how do you decide the methodology to calculate your charge? And do you use proper methodology that can describe charge transfer between the two systems?
Yeah, these charges came from Bader charge analysis. You are correct. We could choose other types of analysis to study the charge. We have a few tests with unary systems where people, not me, but other people from our group, they used other methods such as Millikan charges. I think Viviane's work is with Hirschfeld charges. I don't know if I put it there, but this study here was with Hirschfeld charges. Okay, so one of the main answers is that the behaviors are usually similar for these types of systems with the methods that we tested. I didn't test them myself, but other people did for similar systems. So we go through this path. But you are correct. If we want to study more about charge, we could look into different methods. But I think that the results that I got from Bader charge analysis are distinctive enough, and they are in agreement with what we expect from physical chemistry, from the electronegativities, from the types of adsorption sites. Oops. And that's it. That's the reason we use the Bader charges.
Any more questions?
Thank you, Paulo, for the talk. And just a question about you have the putative global minimum configurations for the isolated clusters, right? So when you adsorb the CO2, have you observed some differences? I mean, on the most stable configuration concerned when the interaction with the CO2, have you observed a case where the most stable configurations changes what is the configuration of the nanoalloy?
That's very cool. Very, very nice question. In these nanoalloys, we didn't get these results. In this specific study, we got one case that is the platinum 55, the pure platinum cluster. The icosahedron structure, it's very unstable and it changes a lot. It deforms when CO2 bends over it. But for the alloys, they do not change. I attribute this to the fact that we chose very stable nanoalloys. This comes from our previous study, and we selected the most stable nanoalloys that we could find. And since they are very stable, they stay like that. But we have results from other students, from Augusto. He saw one of the cases was, I think it was nickel and gallium, right? Nickel and something. And the preference changed from core shell, from one metal to the core and the other in the shell. And this swapped when CO2 adsorbed, which is very nice, but is not an effect that we observed in these transition metals here. But it is important. It is important.
Do we have?
I'd just like to make a comment on the question of Henrique. That's one point on top of that. The question that you would make adsorption on a particle or a surface, it can affect its structure in the way that it can change, yes, but depends on the size. Because if it's like a 13 atom clusters, if you take like, for example, the work of Vivian that she did of silver cluster, it was affected because you can have like 2 or 3 minimums, they are closer by in energy, they can be affected. Once you get in larger systems, like for example 55 or beyond of that, is unlike that the adsorption is going to affect the structure. In the case of 55 atoms of Paulo mentioned about platinum, it's happened that 55 atoms platinum, it distorts by itself from icosahedral structure to a low end structure that with a reduced core size. It happens because the surface build up a very strong strain on the core, and then because of that, it creates some pressure on the core, and the core prefer to reduce the number of atoms from 13 from the icosahedral model to something like 10 atoms, and the atom goes to the surface. And then because of that, when you put like a CO2 or CO over a surface of a local icosahedral structure, 55 watt of platinum, and then you're going to distort because of this effect, because you release part of the pressure. But then we have we published some papers like 2 years ago, when you put some several Lagrange effects on gold particles and platinum particles, you show this effect very clearly. But what's most like systems are smaller systems, like 13, I think up to 30 atoms. These effects can be quite dramatic, especially on the silver, copper, on gold clusters, where they are weakly binding, and those effects are going to compete for the adsorption. But you should have also those type of different minimums nearby energy. Should be nearby, not well separated tunnels on the potential surface.
Thank you, Juarez. That's right.
Do we have more questions? It seems that's not the case, so let's thank the speaker again.